Oxidation reactant, oxidation product, then reduction reactant, reduction product. You are correct. That one is aqueous. I would like you to calculate the E0 cell using two different methods.
That's why we're in class. I knew all this stuff already. I would. I'm supposed to go to that.
You okay?
I just don't think I'll do so much wrong like that.
Oh, that sucks. I'm sorry.
What? Yeah.
Did you guys get what I got?
I didn't know the thing except
They both exist, okay? So you can either take the reduction potential at the cathode and add the oxidation potential at the anode, or you can take the reduction potential minus the reduction potential. Okay, so cathode minus, whoops, that shouldn't say can, it should say cat. There we go. Alrighty, good stuff. All right, page 104. Oh, I need to print page 104. What? No, I need to print it on my OneNote because it's not there. That is 6.3G. Yeah, no, we're good.
Standard temperature and pressure.
Why don't you read that first page while I print this out? So you're reading 104. You don't have 104. You should have gotten it last day. It's the very last page of last day's stuff. Okay?
We should have way faster about it.
So you finished reading? So when does cell potential become zero? When the reaction is at equilibrium. And what does that mean that your battery is like? Your battery is dead. Dead battery. So if you got a dead battery, is there any electron flow? No, there's no electron flow. Can the cell do work? No, it's dead. So the potential for doing work is zero, so the E naught of the cell is zero. So when a cell is at equilibrium, E naught of the cell is equal to 0 volts. Ooh, do we have that formula? Do you guys have your AP formula sheet? It is this color, goldenrod. On your formula sheet, there are 3 formulas for delta G. I have written 2 of them. What could you do with those 2 formulas? We can relate K to E naught. Yes? How would we do that? Move stuff around. Well, I've got delta G is equal to and delta G is equal to. What could I do with those 2 things that are equal to delta G? I could put them together and make them equal. So I have negative RT ln K is equal to negative NF E naught. Now, what can I do with my negative sign? Get rid of it. So if you ever are given an E naught of a cell and you need to find its K value, you can find its K value. If you're ever given a K value and you're asked to find E naught, you can find the E naught. Is good? Yes. What's K? What's K? The equilibrium constant. We're not actually going to do any problems like that right now, but I'm just wanting to mention it so you don't forget that this stuff exists. Yes? Yeah. Yep. No, it's all good. Don't worry. It's a gas constant, but it also applies to other situations as well. Okay. All right. So what happens if the conditions are not standard, but the cell is not at 0 volts, so it is not at equilibrium? Well, it used to be that you would have to calculate the voltage and they gave you a formula for that. They don't ask you to do that anymore. So there is no formula for it. You don't have to worry about it. However, you will be using Q. And I don't know if you remember what Q stands for, but it is the reaction quotient. And how do we write a Q expression? Q is equal to, thank you, Alvin, concentration of products over concentration of reactants at what time? Initially. Okay, so that's our Q. So we're going to use Q to help us figure things out when we are not at standard conditions. We cannot use Le Chatelier's principle. Not. No. Don't. Which makes me sad because that's how I used to teach this when I was just teaching this to regular Chem 12. I would teach it in terms of Le Chatelier's principle because it's really easy to think about it that way. Okay? I'll mention it, but we're going to explain it using Q because AP does not want you explaining in terms of Le Chatelier.
Why does AP have
Okay, because we aren't at equilibrium, we can't actually use Le Chatelier's principle. It's just wrong. I mean, it actually is wrong, but if you think about it that way, it actually works to make your predictions. So if you're doing a multiple choice section and you just want to like predict how it goes, you can absolutely use Le Chatelier to make the prediction. If you're doing a written response, no. Okay? Don't use in written questions. So what we're going to do is we're going to be saying, if I change the conditions in this way, does it make the cell potential greater or does it make the cell potential smaller? Okay, so, you know, our normal copper zinc half cell has a voltage of 1.10 volts. That is only true if we have 1 molar copper and 1 molar zinc 2+. It is only true if we are at 25 degrees Celsius. You are not responsible for predicting what happens to cell voltages when temperature is changed. Okay? You are also not responsible for predicting what happens when gas pressures are changed, but you could use this same Q thing to do that if you needed to. Okay? We're basically just looking at changing concentration to either greater than 1 molar or less than 1 molar. So for an electrochemical cell, E0 is positive, and the K value is very large. And K, of course, is the concentration of the products over the concentration of the reactants at equilibrium, and that is when our when we're at K, E0 equals 0, to be honest. When K is very large, E0 actually equals 0. We are at equilibrium. Am I not plugged in here? Like, what's happening? Why is it not? Okay. Did it get dimmer for you? No, it did not. Okay. Good stuff. Okay. Are we charging? Battery saver. Why are we not charging? Hello. Oh my God. Huh? Hold on. I just need to make sure that this computer doesn't die on me in the next 34 minutes. Why is it not charging? Oh my God, turn off this thing. Oh, shut up. There we go. Oh, are you not plugged in here? You're not plugged in. Oh, I know why. it's not plugged in at all. Okay, here we go. Sorry about that. You go there. Okay. And then you. Then you go there. There we go. Yay! Okay, we are now plugged in. Okay, sorry. Somebody had a question, and I very rudely just said, don't talk to me right now. What were we asking? We don't remember. Okay. Yes. Yeah. I know. I know. I wrote E naught is positive for an electrochemical cell when not at equilibrium. Why? Because nothing's moving. We have no net motion of electrons. Okay? Okay, so does that make more sense now? I realized that I had left that hanging there, that completely confusing statement. Are we good now? Okay, cool. Now, when a system is at equilibrium, Q is equal to K. So the initial concentrations are equal to the equilibrium concentrations when we're actually at equilibrium. I feel like that's just sort of redundant to say that, but I'm saying it anyway. Because what we want to say is as we get closer to equilibrium, Q gets closer to K. Does that make sense? So when Q is very different from K, we are far away from equilibrium. When Q is closer to K, we are closer to equilibrium. Yes?
Q is only dealing with initial concentration. Why would it change?
Because you could measure the initial concentrations now. You could measure the initial concentration 5 minutes from now. Just call your new starting point time equals 0.
Okay.
Yeah? Okay. Now, what we're going to be doing is we're actually going to be comparing Q in different situations. Okay? Now, since K, when we are at equilibrium, is very large, the larger that Q gets, is the value of K getting closer or further from K? It's getting closer. So the larger Q gets, the closer Q gets to K. Yes? Okay. As the cell approaches equilibrium, what is happening to the voltage? Voltage gets smaller. So as we approach equilibrium, Q increases, voltage decreases. We're increasing, so if we increase the amount of product initially, to greater than standard values, now we have a bigger product compared to reactant, yes? Q, compared with standard conditions, is it going to be bigger or smaller? If we increase concentration of products by putting in some extra, let's say zinc 2+, because zinc 2+ is a product. Here's my original Q. This is Q at standard conditions. It's equal to products over reactants. Now my new Q, I've increased P, so it is bigger. So we have our original Q, products over reactants, and we have our new Q, bigger products over reactants. Q has become larger. And if Q has become larger, are we closer to or further from equilibrium? Closer to equilibrium. And if we are closer to equilibrium, the E naught of the cell will get smaller. Now, what if we decrease concentration of P initially? Remember, we have our original Q, which is at standard conditions, Q naught, let's call it. Concentration of P naught over concentration of R, standard conditions. So these would be 1 molar, yes? So actually, to be honest with you, Q naught is almost always, unless something else is weird, going to be equal to 1. Because all our concentrations are 1 molar. So you're going to have maybe 1 times 1 over 1, or 1 over 1 times 1, or 1 over 1. Yes? So Q at standard conditions is 1. So if we now decrease concentration of P, so our new Q, we've made the concentration of P smaller, and we still have the original concentration of R. What has happened to Q? Q got smaller. And if Q got smaller, are we closer to or further from equilibrium? Further from equilibrium, and therefore, is the E naught of cell going to get larger or smaller? Larger. The further you are from equilibrium, the more push there is to get towards equilibrium. All systems want to get to equilibrium. So if you're close to equilibrium, the push to get there, which we can consider like the E naught, potential to get there, is smaller. If we're far from equilibrium, the potential pushing to get there is bigger. Okay? You don't have to go through all this every time. Okay, it's just to kind of get those ideas in your head. All right? Here is a summary showing it in sort of simpler terms. So when Q is equal to K, the cell is at equilibrium and the voltage will be 0. Q is always very large for voltaic cells as they are always highly favored, highly thermodynamically favored. Over here, if a change in concentration causes Q to increase, that brings it closer to K and to equilibrium and 0 volts. So the voltage decreases. Okay, is that a nice summary? Okay, if a concentration or pressure causes Q to decrease, that brings it further from K and thus further from equilibrium and further from 0 volts, so the voltage will increase. Okay, let's take a look at this. Here we have a zinc copper half cell. We have a standard voltage E naught cell of 1.10. If the concentration of zinc were increased to 2 molar, while copper 2+ was held constant at 1 molar, how would this affect the cell potential? Now, I'm going to show you how you can do this and make the prediction, but just don't explain it this way. Imagine that this were an equilibrium system and we increased the concentration of zinc. which way would that cause the equilibrium to shift? So instead of having as much driving force forward, we have more driving force backward than we did before, so the cell potential will decrease. But don't explain it like that. Explain Q is bigger than standard Q. Therefore, we are closer to equilibrium. Therefore, we are closer to 0 volts. Therefore, the voltage decreases. Okay? Pressures work similarly to concentrations when you are affecting E, not cell. Any questions on any of this? You are not expected to predict the effective temperature. Yes?
Yeah, one question.
Yes?
Will it state in the question that it has a very large K value, or we won't say?
You need to know that electrochemical cells all have very large K values because they are spontaneous all the way that way.
And
Yes?
will we ever get a question where we get like a large, like a very large P value? Like how do we know? Like, okay.
No. Okay. The effect of non-standard conditions on battery life, because they can also affect how long the battery lasts. So here we have, I would like you to try, we're first going to look at the cell potential because we've already done that. I would like you to see what happens if we decrease both the copper and the zinc initially to 0.5 molar instead of 0.1 molar. How would that affect the cell potential? See if you can explain that to your partner.
Isn't Q supposed to be like product over reaction?
Oh, it is product over reaction.
Oh.
Yeah?
Oh yeah.
Yeah, cool. What do we think? What would it do to cell voltage or cell potential? Yes? It's going to stay the same because if we take Q is equal to zinc 2 plus over copper 2 plus, and if we say that these are our standard conditions, then we have 1 molar over 1 molar is, of course, 1, but Q nu is going to be 0.5 molar over 0.5 molar, which is 1. So Q is the same, so we are the same amount. We haven't moved closer or further from equilibrium, so the potential will stay the same. To be honest with you, I think it was easier when you just calculated it because there was the Nernst equation and you would throw Q into the Nernst equation and it would make it bigger or it would make it smaller. Maybe if we have time, we'll go over the Nernst equation so you can actually see how the math works out. Okay. How is this going to affect battery life? I don't know. It could either increase battery life, decrease battery life, or have it stay the same. Those are your 3 choices. Discuss.
You're right.
It's so stupid.
Battery will last half as long? Yes? Okay. I don't think you're going to have to explain that. All right? Mm. Mm-hmm. So that's one of the reasons why the reaction is why the voltage is going down. No, I don't know. It doesn't work that way. Go talk to your physics teacher. That's where I go when I get out of my depth. I'm like, talk to your physics teacher. It must be a physics problem. Oh yeah, for sure. We good? Cool. All right, we are now on page 109. 109. You guys are going to like this part. It's just moles. Woo! Moles. Our friend the mole. Now, hopefully you remember that as a redox reaction proceeds, the anode loses mass and the cathode gains mass. Are we unclear on why that is at all? Okay. So what we're going to do is we're going to quantitatively determine how much mass it gains or how much mass it loses. Okay? If we gain 1 gram of copper, what mass of zinc will be lost? Now, without looking at the answer, could you do that question? If I gave this question to you in grade 11, could you do it?
Yeah.
Do it. Do it over on the side somewhere.
I'll do it on my old title page.
There you go. Do it on your old title page. Got to have some use for them, right? I don't know why I filled this in for you guys. I need to remove this. And I need to remove this down here too. Now, if you need to involve electrons, should you be looking at the whole reaction? Because for our next equation, we're going to be looking at electrons. No, you should be looking at, if it talks about copper, you should be looking at the copper half reaction. If it asks about zinc, you should be looking at the zinc half reaction, because those are the ones that involve electrons. So do you see how you could start from grams of copper, convert it to moles of copper, and then we have 2 moles of electrons per 1 mole of copper. And then if you needed the number of electrons, we would be back to our friend 6.02 times 10 to the 23. Is good? Yes. If it's asking you about copper, you should use the copper half reaction. In this case, it doesn't matter because they both use 2 electrons. But if you've got, say, silver and gold, one of them uses 1 electron, one of them uses 3 electrons. So, yeah. Okay? Yeah, but if you use gold, whoops. Yes? Whereas if we have silver, only 1 electron reacts for every 1 silver. Now, if we were going to go balance the overall reaction, we would have to put a 3 here, here, and here, but we still have a 1-to-1 ratio between the silver and the electrons. Yeah, so we have a 1-to-3 gold to electrons, and we have a 1-to-1 silver to electrons. So if you're looking at electrons, you have to be species specific in what you're looking at. Does that make sense? Cool. All right, moving right along, because we never stop. Ooh, electrolysis. Tyler's video is a little bit slow, and it takes a half an hour. So we're not going to watch that one.
Yeah.
Everyone want to watch the Tyler video at 2 times speed?
Yeah.
Okay.
Let's talk about the chemical process of electrolysis. I wanted to try to write the simplest definition.
Okay, you guys are going to tell me if this is too fast, okay? We don't have a worksheet for this. It would have taken me hours to put together, so I did not do it.
I could, so here's what I came up with. Electrolysis is a process where electricity is used to make a chemical change happen that wouldn't happen otherwise. So we have some kind of a chemical change that doesn't happen on its own, but then we can use electricity to make that chemical change happen. Now, electrolysis is often used to take a compound and break it apart into the elements that make it up. We'll look at 2 examples of that in this video. First, we'll look at sodium chloride.
Captions we can do.
Being broken apart by electrolysis into sodium metal and chlorine gas. And just FYI, this is an unbalanced equation. Then we'll look at an example of water being broken apart using electrolysis into hydrogen gas and oxygen gas. So let's get started by taking a look at this reaction. So here's an unbalanced equation for the electrolysis of sodium chloride. Now sometimes people ask me, why is it Cl2 and not Cl? Well, that's because Cl, chlorine, is one of the diatomic elements. These are the diatomic elements. And the diatomic elements always form groups of 2. They always pair up together. You never find just one of these atoms alone by itself. So this would never just be Cl. It would be Cl2 instead. So the equation we've got here is an example.
So what is one reason why we might use electrolysis? Is 2 times too fast? To break apart a compound. Now, would this break apart on its own? No, why not? It's very strongly attracted, but also the Na in NaCl has given away its electrons, so it has a full stable shell. And the chlorine has accepted electrons, so it has a full stable shell. Does chlorine want to give an electron back to sodium? No, that is thermodynamically unfavored.
Example of an oxidation-reduction reaction. Electrons are moving between atoms in this equation. I want to understand how they're moving and where they're moving. And in order to do that, we got to write oxidation numbers for the different elements in this equation. So check it out. I got some information.
Okay, you tell me, who are the oxidation numbers for NaCl, NaCl? Oxidation number. Positive 1. Negative 1? 0? 0. Okay, cool.
Information here that will help us write oxidation numbers for these elements. We can do this really quick. So NaCl here is an ionic compound, sodium and chloride. Na is in group 1a, so it's always +1. Okay, Cl, chloride, is one of the halogens here, usually -1, positive with oxygen, definitely -1 here. And then on this side of the equation, we have sodium and chlorine on their own. They're elements by themselves. They're not bonded to any other elements. So Na over here is going to be 0, and Cl2 over here is going to be 0 as well. Okay, so those are the oxidation numbers for these elements. Now, to understand...
So who got oxidized and who got reduced? Na got reduced because its charge got smaller. It got reduced. And Cl got oxidized. Good.
And how the electrons move, we got to take a look at the changes in these oxidation numbers. We'll use this information to help us out. So let's take a look at sodium here, Na. On this side of the equation, it's +1, and then over here, it's 0. So its oxidation number goes down. So that means that it is undergoing reduction. It is gaining electrons. So sodium is reduced here from +1 to 0. And then Cl goes from -1 here to 0 over here. So its oxidation number is going up. It is undergoing oxidation, and it is losing electrons. It's being oxidized from -1 to 0. So sodium is reduced, gaining electrons, and chloride is oxidized, losing electrons. Now there's something really important about this process, and that's that this process doesn't happen on its own. Sodium chloride is also known as table salt, and you could keep table salt in your kitchen for hundreds of years.
Pause. I would like you to go to your chart and see if you can see why, according to your chart, it doesn't happen. Are they on the same side? Where is sodium? Way down here. Okay, so here's sodium. Where is chloride? Whoa. Whoa. Up here. Ah. Yikes. Now, do you remember last day we said electrochemical cells go like this? Right? We have our cathode, we have the reduction, and then we have our E0 cell. That's how much it gives off. And then we have our oxidation, and that is a Voltaic cell. Well, if you look at what we've got here, we're starting with Na, and it's going to go forward. Yes? How much energy how much potential do we need to put in? That much potential, the difference between those two. That's how much we need to put in to make this reaction go. Okay? And then you'll see that here is our reactant for the, is this going to be the anode or the cathode reaction? It's going backwards. So that process is Oxidation, and oxidation occurs at the anode. Yes? So we have reduction at the cathode. We have oxidation at the anode. And so a voltaic cell goes like that. An electrolytic cell the reduction is down below. This is our cathode. This is our anode. And then we have oxidation. And there is our E naught of the cell. Now this is going to be, even though it looks like it's going down, this is going to be a positive thing because that's how much it's giving off. This is going to be negative because that's how much you have to put in. Okay? All right, back to Tyler.
And it's never going to separate out into sodium and chlorine gas. It's just not going to happen. This process doesn't happen on its own by itself. To use chemistry terms, we can say that this process is not spontaneous. Spontaneous process is something that happens on its own.
Instead of not spontaneous, what are we going to say? Not thermodynamically favorable. Excellent.
Now, a big part of the reason why this isn't a spontaneous reaction is because sodium and chloride over here are really happy with the number of electrons they have. Sodium doesn't want to gain more electrons. And chloride here doesn't want to lose electrons. They're totally set right here. So we have to force this process to happen. And that's where the electricity part of electrolysis comes into play. The electrical energy from a battery can force this process to happen. So here's our battery. And a battery has these two sides, the positive and negative. The positive side of the battery pulls electrons in, and the negative side of the battery pushes electrons out. So these two things can force this process to happen. So chloride doesn't want to lose its electrons. But you know what? The positive side of the battery just pulls electrons away from it, right? It's like, you don't want to lose these electrons? Tough. I'm just going to pull them away from you. And the negative side of the battery that pushes electrons out, it's going to push electrons to sodium. Sodium doesn't want to gain electrons? Too bad. The negative side of the battery is going to push electrons to the sodium, making this process happen.
Did you catch that?
Yes.
Yes? Okay, cool.
So now I want to show you the device that we use to do electrolysis and make this process happen. And then I want to use our atomic vision to see the atoms and electrons and how they move during this electrolysis process. So here's a picture of the device that we use to make this process happen. This is called an electrolytic cell, and it's got a couple of different parts. First, we got this container that's full of the sodium chloride. Then we got a battery, and the two sides of the battery are hooked up to what we call electrodes. The electrodes put electrons into the sodium chloride, and they pull the electrons out.
Now, very often in an electrolytic cell, the electrodes are inert. Not 100% of the time. We'll look at some cases where they aren't, but very often they are inert, so they will not be involved in the reaction, okay? So we're only going to be looking at the substance in the beaker.
And then finally, the sodium chloride here, it's not just like the powdered table salt that you're used to from the kitchen. This has got to be molten, liquid, melted sodium chloride. Sodium chloride doesn't melt.
Why do we need to melt the sodium chloride? Because we need the ions to be able to move. Which direction will the cations move? Towards the cathode. And which way will the anions move? Towards the anode. And I'd like you to look at this right now, and I would like you to decide which of these two is going to be the cathode and which is going to be the anode, based on which terminal of the battery they are attached to. So which direction are electrons moving? Are they moving from left to right or right to left? From left to right, because the positive terminal is sucking electrons in and the negative terminal is pushing electrons out. So if we're pushing electrons over here, what's going to migrate towards this electrode? This electrode is now going to be full of electrons. Are we going to have anions migrating there or cations migrating there? Cations, because they're attracted to all those lovely negative electrons. They want to be able to gain those electrons. So if this is the one that cations migrate towards, what is that electrode called? That is the cathode, and that would make this one the anode. It can be aqueous, but it introduces another level of complexity because water can be oxidized and reduced, and now you have to make a choice. Is it the sodium ion or the water that gets reduced? Is it the chloride ion or is it the water that gets reduced? Okay, and we'll look at that next day. All right. Yes. What is what? Molten means melted. So you have literally melted it. It is liquid. Okay, so it's liquid. No water, just liquid. Okay?
Until about 1500 degrees Fahrenheit or 800 degrees Celsius. So it's got to be super, super hot. And this device has to withstand really high temperatures. The sodium chloride has got to be molten for the electrolysis to happen. Now let's zoom in on this a little bit more. If we could zoom in to the sodium chloride millions and millions of times, this is what we'd see. The sodium chloride is molten or liquid, which means the sodium and the chloride ions have come apart from each other and they're in constant motion moving around in this container. Now, here are the electrodes. This is that one, and this is that one. These electrodes in the diagram here are way, way, way closer together than they should be based on this. This is definitely not to scale, but I wanted you to be able to see both of the electrodes. Now there's another important part of this electrolytic cell, and that is the battery. The diagram that I put here shows the direction that electrons move. Electrons move from here into the battery, and then out of the battery into this electrode. So we can give...
That's the other way you could tell which one is the anode and which is the cathode, because electrons always move from the anode to the cathode.
names to these two electrodes based on how the electrons are moving, okay? The electrode over here we call the anode. The anode is the site of oxidation. Oxidation is happening in here because the anode is pulling in electrons, because this is the direction the electrons move. Now over here, we have the cathode. Reduction happens to the cathode. The cathode pushes out electrons because this is the direction the electrons are moving from the battery. So we got the anode and the cathode. We got the battery, the electrodes, and the sodium chloride. We're ready to do some electrolysis. I'm going to get rid of a few of these ions to make the process a little bit clearer. Okay, that's a little bit clearer. So now we hook the battery up to the electrodes, and this is what happens. So this cathode here is connected to the negative side of the battery, so that means that it's going to have a negative charge. These positively charged sodium atoms are going to be attracted to the negatively charged cathode because opposite charges attract. So we got this Na plus moving over to the negatively charged cathode, and electrons, as we said, are being pushed out of the battery into the cathode, and this electron is going to be given to the Na plus ion, and gaining that electron is going to get rid of the charge on that Na. So it's going to turn this into a neutral sodium atom. The same thing is going to happen to this one over here. It's got a positive charge, it's attracted to the negative cathode, moves over here, an electron gets pushed from the battery, it goes into the sodium ion, and gaining that electron causes the sodium to lose its charge.
We following that okay? Okay.
So now we have two neutrally charged sodium atoms. Now over here at the anode, the opposite thing is going to happen. Electrons are going to be pulled out of these ions. So we got this
Yes. Yes.
chloride over here. It's attracted to the anode because the anode is hooked up to the positive side of the battery, and this is negatively charged, so it's going to be pulled over here. And the anode is pulling in electrons. So one of the electrons from the Cl minus is going to be pulled up towards the battery, and that is going
I'm sorry, I just have to say, isn't it cool how he has that little electron sitting under there just ready to go? So anyway, I appreciate his craftsmanship.
to cause the negative charge to go away because it's lost one of its electrons. And then over here, this Cl minus is also going to get attracted to the anode. It's going to lose one of its electrons, it's going to get pulled up here towards the battery, and that is going to cause this to lose its negative charge. Now we said that chlorine here is one of the diatomic elements, so that means that we're never just going to find one of these atoms on their own. As soon as they don't have a charge anymore, they're going to pair up to form a Cl2 molecule. This is gas, and it's actually going to float away. So that's how the electrons move in this electrolytic cell.
Yes. Yeah.
So here's a diagram of the process that I just showed you. I want to use this to write half reactions for what's going on at the anode and the cathode. So oxidation happens at the anode and reduction happens at the cathode. Let's write these half reactions. So over here at the cathode, we start out with Na1 plus. That gains an electron, plus E minus, the symbol for electron, and that gives us neutral sodium, Na, without a charge. That's how we know it's neutral. Now over here at the oxidation half reaction, I'm going to write this a little bit incorrectly first, and then I'm going to fix it. Okay. So here we start out with two Cl1 minuses, okay? Two Cl minus. And then what happens is these lose two electrons, 1, 2, get pulled up to the battery. So I'm going to write minus 2 E minus. That's incorrect, but I'll fix it in a minute. And that gives us a molecule of Cl2 gas. Now what's wrong about this? Well, you can't subtract things in a chemical equation, even though it makes a lot of sense. So to make this correct, I have to put these two electrons on the other side of the chemical equation. So here is the correct version, where I just moved the electrons over here. And this is the correct way to write the oxidation half reaction. Now that I've written the oxidation and reduction half reactions, I want to show you how we can put them together to get a reaction for this whole process. Now let's combine these half reactions that we just wrote.
Do you know how to combine these two half reactions to get an overall reaction? Yes. What would you have to do before you can add them? Multiply the top one by 2.
We're going to add or combine these half reactions together. They have to have the same number of electrons, but they don't. Right now there's 1 electron here and 2 electrons here. So to fix that, I'm going to take this reduction half reaction and I'm just going to multiply it by 2, just like it's a math equation. And that is going to give me this new reaction. I just put a 2 in front of everything, distributing it across the reaction. Okay, so there's my new reduction half reaction, then here's my oxidation half reaction. Now that they have the same number of electrons, I can add them together. And this is what I get. I take everything on this side of the arrow and put it on one side. I have my Na, my 2 electrons, and my 2 Cl on this side. And then on this side, I have my Na, my Cl2, and my 2 E minus. Now there's still a little bit more that I have to do before this equation is totally finished. If there's anything on both sides of the arrow, we cancel it out. So there are 2 electrons here and 2 electrons here. I'll cancel those out. And then I have 2 Na plus here, and I have 2 Cl minus here. I can combine those together to make NaCl. So my final equation is going to look like this: 2 NaCl, and then on this side, 2 Na plus Cl2.
Ooh, I don't like that. I would keep them as separate ions. I would keep them separate and call them liquid. Okay, I'm not that happy about that because they are separate from one another.
And you'll notice that I've also put in these parentheses to show the physical state of each of these particular compounds. This is liquid because it's so hot, it's molten. The Na is also liquid because it's so hot. And the Cl2 is gas and just floats away. So let's just pull everything together that we talked about. Here is our final equation for the electrolysis of sodium chloride. This happens because sodium gains electrons and is reduced. This happens at the cathode in the electrolytic cell, which pushes out electrons. It's where reduction takes place, and it's where sodium gains these electrons. Here is the half reaction for the reduction of sodium. Then chloride loses electrons. It undergoes oxidation, and this happens at the anode in the electrolytic cell. The anode pulls in electrons, oxidation happens there, and here is the half reaction for chloride losing electrons and getting oxidized.
I would like you guys to see if you can calculate the E0 cell for this electrolytic cell, please. There's nothing different about the equations. Just do it exactly like you did before. E0, red cat, plus E0 oxan, or E0 red cat minus E0 red an. Yes. Yes, I can pull up Tyler's diagram.
No, it is.
Yes. Did I do it wrong? Oh, 2.71. I'm sorry. I was trying to do it from memory. That didn't work so well, apparently. So that would be 4.07? Excellent. How are you guys feeling about electrolytic cells? They're pretty much like electrochemical cells, except for they go backwards. Okay, we'll get into the more complicated stuff next day. Your homework, I would like you to do, where are we at here? Pages 99 to 101 and 107 to 108. Okie dokie.
When we were asked to go back to look at the oxidative numbers, I realized that I'm missing my, but from 5
Oh.
to 6.
Okay, let's see what.
If you bring back up. Well, I need to get better at
Just 5.
There we go.
He's driving.
I'm not gonna be here tomorrow.
Okay.
For my dance show.
Okay.
So let me know what's good.
Yeah, so I think I'm not entirely sure what we're going to get through tomorrow. We're going to do electrolytic cells. So I would assume that it would be. Sorry, let me just put this back together so I can show you. I assume it would be. Sorry. Just so I can flip the pages properly. Probably going to get through all of this tomorrow and maybe give you some time to practice. And I'm going to have some stuff tomorrow. Are you away from school for the showcase? I'll post it online. Okay? Yeah. Cool.
He's